Hello everyone and welcome to my presentation. My name is Đức Lê and I am an undergraduate student at RIT. For the past 1 year, I've been working on this project about optical rotation of a 2-ion crystal in a linear point trap, together with Dr. Pan and Professor Bhattacharya at RIT, as well as our collaborators Professor Ozawa and Professor Udem. So let's begin by talking about the simplest case of ion trapping, which is done for single ion. To trap an ion, we will need an effective trapping potential, which is formulated in 3D as a harmonic confinement with coefficients alpha, beta, and gamma for the x, y, and z components. For the trap potential to be purely confining, these three coefficients have to be bigger than 0. However, there's another condition, which is Laplace's equation in the electric field theory, which states that the sum of the three coefficients have to be equal to 0 for the field to be physical. As a result, any static electric field can never trap ions, and in fact, the electric potential is always shaped like a saddle, and you can never trap anything in the middle of a saddle like this. So the solution is implemented in the point trap, which is to rotate this saddle potential to create an effective trapping in all three directions at some point in time. So for example, at this time, the field is confining in the y direction and not confining in x direction, but after some time it will be confining in the x direction and non-confining in the y direction, which enables ion trapping. So how does an ion move in such a complicated alternating trapping potential? So the answer is that there are mainly two motions that we can observe. The first one is a slow circular precession, which is this motion here, also known as the circular motion. The frequency of this circular motion is determined by the properties of the trap, Q and A, where Q is related to the RF rotating field and A is related to the static field. Across that motion, there is also a micromotion, which is a rapid but small amplitude motion, and that motion is attributed to the RF field, and in fact the frequency of the RF motion is exactly the frequency of the RF field. Now that we have had an idea of how ion trapping work, let's move on to the specific setup of our experiment that we have been studying during the course of our research, which includes a linear point trap and a cooling laser beam. So the point trap will try to trap the two ions using first the DC end cap, which will provide a static voltage to confine the motion across the z-axis. And on the xy plane, there will be an RF voltage that will trap the ions radially. And the RF trapping frequency that we use here is going to be 70 megahertz. So the two ions can be trapped in place by the point trap, but we also want to do other things with them as well, like to rotate them. So to do that, we will shine a laser beam to the two ion system. The beam will be offset at the position x0, y0, and z0, and it will also be oblique, characterized by the azimuthal and radial inclinations phi and theta. And finally, the ions we are using in our experiment is the beryllium plus ion. Next, we try to establish a numerical framework that aims to describe, to explain the behavior of the two ions under the influence of the linear point trap as well as the laser beam. So there are 5 main forces in our model: the trap force, coming from the linear point trap and the optical force. Those two are tunable by changing the trap parameters as well as the beam power and orientation. There are also three more forces: the Coulomb interaction between the two ions, thermal fluctuations, as well as the damping force. The main takeaways from our numerical analysis is that we are able to tune these trap and laser parameters to set these ions to rotate. And this rotational motion is characterized by a non-uniform orbital motion. As you can see here in the change of the XYZ coordinates in time. If this had been uniform, this will be purely sinusoidal, but as you can see here, it is not. So because of that, the ions will spend some more time in some positions than other, and this matches very well with the experimental result. The black and white portion of this image is the experimental result. You can see the ions will hang out more in this position rather than this position, because which leads to the difference in the brightness. And this color part is our numerically simulated result, and it matches very well. With quite a complete numerical framework, we then move on to find an analytical model that can describe the properties of the orbit of the two-ion system. To do that, we need to do some simplification, namely to approximate the Gaussian intensity profile of the laser beam into first order with these coefficients mu, nu1, nu2, and nu3. With that, we were able to find the shift in the center of mass of the two-ion system, and then we were also able to find the orbit diameter of the two-ion system. And as you can see, it is dependent on the RF trap parameter Q and the DC trap parameter A, and as a result, it can be tuned accordingly. Another result that we found analytically was the position of minimal ion velocity, which corresponds to these bright spots on the experimental data, and here is that formula. So the analytical result found in the previous slide turns out to be very similar to the numerical result, despite the simplification that we made, and that includes the diameter and the offset of the center of mass. Another very important analytical result that we managed to derive was the rotational frequency of the two-ion system. Here is the formula for the average rotational frequency. As you can see, it is contributed by the RF frequency, the beam power, which is implicit in F0, the beam offset implicit in the coefficients nu1 and nu2, and the azimuthal and radial inclination of the beam orientation. There's also quite an intuitive negative contribution of gamma, which is the damping force. And we were able to predict that initially, when you increase the beam power, the rotational frequency will also increase. But after a certain point, because of torque saturation, this frequency will drop as you increase the beam power, and it is the analytical result follows very closely to the numerically simulated frequencies. And as you might recall, this rotational motion is non-uniform, so we were also able to derive an equation that describes the fluctuation of the angular velocity across one full rotation. And we were also able to predict at which beam power will the two ions rotate the fastest. And because during our numerical analysis, we found that there are cases where the two-ion system can rotate and there are cases where they cannot, we also attempted to find an analytical rotational condition. So the first condition has to do with the laser parameter, where we found that for a set beam offset and orientation, there will be an upper bound and a lower bound for the beam power to allow rotational motion. There's also an additional condition for the trap parameters, which is this ratio between the DC and the RF trap parameters to allow for rotational motion. And we were also able to expand our numerical framework to describe the behavior of system with more than 2 ions. So here are some of the figures that we obtained during our numerical analysis using the same model with the same force contributions. And we try to overlap it with the experimental results that we received from our collaborator. And as you can see, the numerical orbit matches very well with the experimental result with the same diameter of the result and the distribution of the ion across that orbit. So in conclusion, we have detailed a numerical model for the optical rotation that matches very well with the experimental result. We were also able to derive an analytical method that gives very simple equations to describe the key properties of the 2-ion orbit, including the diameter and the rotational frequency, along with the rotational condition. And the fit between the numerical and experimental orbits for complex cases with more than 2 ions were also very encouraging. And we expect our research to find use in a wide variety of fields, including rotation sensing, observing Hawking radiation in acoustic analogs of black holes, and also to engineer micromotors. And I would like to thank Professor Bhattacharya and Dr. Pan for their guidance and advice during the course of this research, and our collaborators for providing us with very insightful experimental data. Thank you for listening to my presentation, and I would welcome any comments or questions in my email address, which is below in the description.